Okay, so this is probably the right talk for the end of the day because you're all tired, and this is going to be a really simple talk, right? Real simple. So what's this talk about? Well, the thing is that a lot of times when people try to look at getting high-performance code working in machine learning, they somehow all of a sudden forget about the fact that they actually have machine learning data. And a lot of high-dimensional sparse problems, for instance, have power laws. And I think there's even a paper about the power law discovery. But essentially, you can pretty much assume that any high-dimensional data you'll be dealing with will have some form of power law property. And it's slightly surprising that people haven't used this a lot more yet. And this is actually, and basically what I'm trying to point out in this talk, based on two vignettes, namely one for a recommender system and one for a factorization machine, that by actually exploiting this, and by exploiting it both on the computational side and also on the statistical modeling side, you can make your life a lot easier. You can make things fit in memory that otherwise wouldn't. You can make things go a lot faster, like 1 or 2 orders of magnitude faster that otherwise wouldn't. So by all means, please take advantage of it, and you'll get a lot higher performance. Okay, so that is, in a way, the talk, and if you remember that, you can fall asleep now. Okay, well, not quite, but here's a really gorgeous slide. This is a slide from, a computer website called The Register, and what they did is they discussed various memory types, and actually, it's a really, really great slide. So what it does is the following. Basically, up here, here's the CPU. And here is the stuff that you've probably never used, storage, area networks, tapes, and whatever. But basically, usually, what you actually have is SSDs, hard drives there, then there's the memory, and here's the CPU. Now, the point is that all those things have very different capacity, and they have very different speed. Now, this sounds kind of like the really boring, horrible hardware talk, but once you actually look at the fact that we're talking a couple of orders of magnitude, you can start to realize that you actually want to take advantage of this when you design your algorithms to get better performance. So just a little bit of ballpark figures. So your CPU cache maybe has 10 megabytes, and that's a pretty good CPU, and it operates at about 1 nanosecond scale. I'm simplifying a lot here, but just to get sort of the ideas across. On the other hand, if I have my memory, well, we go up by 3 orders of magnitude. And we're going up in terms of speed of access by 2 orders of magnitude, right? So those two things don't always scale at the same speed, but sort of, kind of. Now, if you go to a solid-state drive, again, you're going up by 2 orders of magnitude in terms of speed of access. And in terms of storage, maybe bit under 2 orders of magnitude. Then, well, to the hard drive, well, all of a sudden you're hitting 3 orders of magnitude access speed and about 1 order of magnitude storage, and so on. By the way, fun fact, why have hard disks not gotten any faster? Well, it's not that you couldn't position the head much faster. You can do that at near instant speeds. But the thing is that the hard drives rotate. And the time is really given by the time it takes for the disk to rotate once around. And you can't really make them much faster because otherwise they explode. And this actually used to happen some time ago when they didn't have that much under control. So there are certain physical limits that constrain things in interesting ways. But basically, when you design your statistical inference algorithms, by all means, take this into account. Well, I'm by no means the first one to have done this. Probably this is one of the first ones to really popularize this is Jeff Dean. So in the slide numbers, every engineer should know. And there's an updated version of this, and I'm not going to go into all the details here, but basically, if you normalize the most basic operation to about 1 second, then here we are talking about, well, a decade to send a network packet between 2 different server centers. So that tells you that by doing stupid things, you can actually really kill performance. So ignorant code can kill performance by many orders of magnitude, and so there's absolutely no point in running stupid code faster on 1,000 machines if by a little bit of better engineering you could actually run it on a single machine. Okay, and by the way, I've done this too, right? So we had cases where we ran code on 5,000 machines, and then with better math, okay, you get it down to 8, same time. Okay, so let's put a little bit of context behind this because, well, talking the abstract is no good. Let's look at something like recommender systems. And I've deliberately picked a really, really dumb, simple algorithm. Anything that we've seen before today could be used for that, but this is really just to prove the point. So let's say I have users and movies. I have some very simple function class, which is basically just matrix factorization. So I have the inner product between a user vector and a movie vector, and, well, I have my biases. Okay. I also picked the simplest of all loss functions, just least mean squared loss. I could pick something much fancier, but basically the point is I actually want to minimize some loss, maybe subject to some penalty. So I might have a penalty like so, basically, which just tells me that the parameter should be small. Or I might want to weigh it accordingly. So let's ignore technical details there. But what I get is actually very, very simple update operations. Again, I could have projections, prox operators. I could make this much fancier than what I have here. But basically what this is just take, let's say, the user vector, shrink it a little bit, and then update it by essentially something aligned to the movie vector times the discrepancy. Likewise here. So this is really simple. You can take this and you hand it out as a programming assignment for, you know, a grad student class, Introduction to Machine Learning, and you give them 2 weeks, and this is going to be 1 of 5 problems, and they happily come back with a solution. Because, hey, everybody can implement 2 lines of MATLAB, right? This is not hard. It's really easy. And this ought to be cheap, except that it isn't. So the problem is really in the memory subsystem. So this operates on a real computer where data isn't instantly available, but I actually need to go and get it somewhere. So let's put some numbers behind that. Let's take a small problem like the Netflix contest. So we have 100 million samples. Let's say we have 2,000 dimensions. Let's say we do about 30 stochastic gradient descent iterations through the data. Okay. So what can happen? Well, we have 100 million times 2048 times 30 times 4 times 8 byte, because I'm doing the stupid thing and storing it as double, burst reads. Right? So burst reads basically means once I actually start reading at one location, all the subsequent reads are a lot cheaper. They're about a factor of 10 cheaper. And I also need to perform, well, 100 million times 30 times 4 random lookups, because I basically need to pick the first location, and after that all the subsequent reads are cheap. Okay. So then if you plug in some numbers about, you know, typical hardware that you can get, this is a reasonably high-end server, you get about 1 hour and 15 minutes of runtime. Actually, if you can code this up straight away and get your Netflix solver done in that time, you're a pretty good programmer. So, and this sounds like, you know, you can't really beat it, because what I've done here is I've just plugged in numbers for the memory interface. I've assumed that my CPU is infinitely fast, right? And I've basically just plugged in numbers for the memory interface, and I'm stuck at basically, you know, 75 minutes. On the other hand, we managed to actually squeeze it down to less than 10 minutes, and so the obvious question is, how can you do that? And so if you want to read the paper, this is a Rex's paper from last year, it also has a lot more other details in it about differential privacy, how you can do that in practice, how you can make it personalized, and again, how you can make it go fast. And without going into a lot of details, because I won't have time, this can be achieved by stochastic gradient, large model dynamics, and actually applying it to, in this case, recommender systems. But since the point of the talk is to talk about head, torso, and tail, let's actually look at what we have. And this is on the Netflix dataset, and if you look at, let's say, the Yahoo Music dataset, you get the same thing. So what you get, something very simple. You have a lot of ratings for a very small number of movies, because those are the movies that everybody watches, that everybody reviews. It's like the Star Wars. Then you get stuff like, well, in the torso, where you get, well, movies like Life is Beautiful that a reasonable number of people have watched, but not that many. And then here you get all the movies that nobody really watched, and they maybe have 1 or 2 reviews. Now, this is usually considered as, well, being really terrible, because what you would usually assume is that, well, power laws mean, well, I have very large footprint, everything is really expensive, I need a lot of memory, a lot of storage, life is bad for me. But actually, you can take advantage of power laws, because power laws mean that the matrices that you're dealing with, let's say the recommender matrix of users times movies, isn't just sparse. It's sparse with a lot of structure. And you want to take advantage of this. So let's look at it. Well, this really means I will have a lot of requests to know about the movies that are very common. And this is going to mess up my memory footprint. Now, in the context of something like, the commonly available recommender data sets, that's actually not a big problem, because let's say 20,000 movies in 2,000 dimensions, that's about 160 megabytes. So this isn't really an issue here, but this is going to kill us. I'll afterwards show you a problem where this really becomes an issue and where you can actually fix it with good co-design of statistics and engineering, but right now we want to deal with this. So what do? Well, the first thing you notice is you actually usually don't have just multi-core, you have multiple sockets. And one thing that you particularly want to worry about is something called false sharing. False sharing basically means if data is in one cache, the other processor wants it. So it first has to get evicted from the cache, goes back into main memory, then the other processor grabs it and pulls it out. During that time, both processors are stuck. If you ignore that, you pay about a factor of 2 or 3 in performance. So don't be that guy. So the other thing is you want to stratify the data appropriately. And this is, again, where statistical modeling helps you. Because the one set of variables that is reasonably smallish is the set of movies. Set of users is really large, and we can assume that it grows a lot. And it also makes sense in terms of optimization, because the key information, so conditioned on the movies, we can essentially assume that all the users are exchangeable. The ratings for the users are exchangeable. Likewise, the other way around. So we just need to make sure that we get that setting right. So you stratify by users. This means you process one user at a time, and this means also that already we don't get cache misses anymore for the users because we get all their recommendations at once. The second thing is you make sure that you keep the frequent movies in the cache, and you do that for instance, by blocking all the common frequent movies together. And again, that's really easy to do because finding the most frequent movies doesn't mean that you have to go through the entire data set. The last thing is you ensure cache affinity such that different movies are used on different sockets. If you do all of that, then you get really nice cache performance. So the numbers that I can show you here are basically on the left-hand side, this are stochastic and version with proper cache properties. And essentially, you get like a 3% level 1 cache miss rate and about 1% for level 3. And GraphG has numbers that are about a factor of 5 higher. So the reason for that is, to some extent, the way how GraphG partitions the data. The reason why we picked GraphG as a comparison is because it was the fastest open source solver that we could get our hands on. All the other solvers were closed source. And if we wanted to actually analyze everything in detail, having the source code really helped. So GraphG basically partitions graphs in a checkerboard manner. And this means, and then it goes off and basically processes one block at a time and produces corresponding updates. That's a very neat idea. The only problem is that you only get mixing and exchange of parameters whenever you move from one block to the other. What we did instead is we basically partition in such a way that we have one user at a time, and so you get much faster mixing. It's also much more cache friendly. And I'll show you afterwards that this is exactly reflected in the convergence properties as well. But before I do that, let me first show you speed. So a couple of details here. So this is us. This is on Netflix. This is Yahoo Music. This was unfortunately the largest recommender data set that we could get our hands on. It's not very large, it's only 250 million recommendation pairs. And this is linear scaling in the dimensionality of the model. So when people tell you that their solver for Yahoo Music or Netflix is fast, they usually tell you something that's in the order of maybe 50 dimensions. We went all the way up to 2,000 dimensions, just to make it a little bit more interesting. These are other solvers, and GraphLab is actually pretty good. It's only twice as slow as ours. They did actually a pretty good job optimizing GraphG, because I think that's where they started. All the numbers are on Amazon C4 8X large, so that's basically their most expensive instance. And the interesting part here is bitmap. So there's this black line here, which is a GPU code. And basically, what this just shows you is that with proper engineering design, you can actually beat a GPU code rather handsomely on a CPU. Now you're wondering, why on earth are we not seeing bitmap here? Well, it ran out of memory. This is the other advantage of using a CPU rather than a GPU. Now, could you use some of those things on a GPU? I think you could, and this is actually one of the things that we will surely be looking at in the future. But this is really just to get the point across that by doing careful engineering, actually there are many cases where CPUs have quite an advantage. Sparsity is one of them. Now, back to the convergence issue. So what you see here is three curves. The blue curve is GraphG, which has those macro blocks, and it only mixes once it's done with one row of the checkerboard. The red line is our solver, and you can see two things. First of all, it's faster. So basically, the little triangles are much more closely spaced together. That's the same number of iterations. The second thing that you see is it converges much faster because it actually traverses the data in a better way. Now, you might wonder what the green curve is. So this is the differentially private version of the solver, which basically adds Gaussian noise to it. And it does so in a rather interesting way by recycling, essentially, the noise to avoid drawing lots of Gaussian random variables, which otherwise would be quite terrible. Okay. So before we move on to factorization machine, let's do a quick sanity check. So what would you really expect, right? So C4 8X large has about 200 gigaflops. It's like 198 something, so at least these are the numbers that I got from Geekbench, so somebody ran the stuff. And if you were to do sparse matrix vector multiplication, you'd probably get about 10, maybe 20 gigaflops. So that's because usually sparse is a lot more expensive than dense. So an M40 GPU will give you about 6.5 teraflops for dense SGEM. So these are numbers that NVIDIA gives you. So basically, we're about, a bit over an order of magnitude faster than what the largest CPU instance currently gives you. Now, on the other hand, if you run a very similar model to what I just showed you, which is basically a sparse high-dimensional autoencoder, so Scott Legrand did this in TensorFlow, then after a little bit of careful calculation, I can walk you through that offline, you get something that amounts to about 10 gigaflops, right? That's not very good. So in other words, out of the 6.5 teraflops, you're really getting really, really awful utilization. Now, so basically, this is like 0.2%. Amazon's DSS TNE, which at least does a better job, arguably, in dealing with sparsity, gets about 1% utilization of the GPU. I think that's still quite awful and very much improvable. But the key point why both of them are so awful is that they don't really exploit the fact that you have power law properties in the data. If they did that, I think you could easily squeeze out another order of magnitude. So for reference, we get about 40 gigaflops. So remember, 200 are peak. So we get about 20% of peak performance, even though we do sparse. That's decent. Basically, what you can easily see is you get basically data times dimensions times the fact that you have multiplies and adds, and they count separately, and then the F forward prop and back prop equivalent operation, basically computing the rating and then doing the updates. So, takeaway from this is a lot of sparse codes that are written for linear algebra first and foremost ignore the fact that machine learning data is special. So machine learning data is really a lot nicer than your run-of-the-mill generic sparse data. And what you can therefore do is you can actually put the head of the data into a CPU cache, you put the torso into RAM, make sure you do nice things with it, and then the tail goes into out of core, maybe on a solid-state disk, and you use statistics to keep that small. And this is actually kind of nice because a lot of the sparsity and dirty models, all those approaches essentially tell us how to get rid of a lot of parameters that we don't need. And now, what we're seeing is from the system side, exactly that same trick is also going to help you actually scale things to large problems. And don't worry, stay tuned for the next vignette where I'm actually going to go into this in detail. But basically, what you want to do is you really want to do whole system optimization. You have a larger footprint, and you use then SSD, RAM, cache, and the GPU, and you just use the main memory as yet another caching layer. The key question is going to be how to automate this. Because, well, we can happily go on and write another half a dozen papers for a specific problem. Here's how we specifically lay things out, and here's how we get 1 or 2 orders of magnitude improvement. That's fine, and you can graduate students mass production-wise this way, but that's not interesting. The interesting thing is, how do you go and specify a model? You possibly specify, hey, I believe that these types of attributes are going to have a certain type of distribution, or maybe you can even easily detect it. I mean, it's not that hard to detect power loss. And then use a data-dependent system optimization to actually solve it. So I think this is where the really interesting research is going to be. And now, just to contradict myself, I'll show you another vignette of how to do it. Okay, so this is dealing with a tail. So the issue is basically if you do something like, computational advertising, that a linear model isn't really enough, right? So if you search for machine learning on Google, then Google Ads team, they probably still need a lot more machine learners. I think they already have a couple of hundred, but I think they can always use more. So one very convenient way of going nonlinear is by using something called a factorization machine. And a factorization machine doesn't actually do anything particularly magic. What it simply does is it's a polynomial expansion that, of course, therefore goes beyond a linear model. Now, of course, if you have let's say, a quadratic or a cubic or a higher order model in a very high dimensional sparse data, then you would need monstrous matrices, right? After all, if you think about it, right, this is a simple linear term. Here you would possibly need a quadratic matrix, and there you might even need then, a corresponding third order tensor. And you can immediately see that if we even have just 1 million dimensions on any of those sides here, this is fatal, right? So what Steffen Rendle did, and that's very ingenious, is he said, well, actually, let's just make a low-rank approximation of these objects. So remember, dirty models, that's effectively what he's doing. So he's basically assuming that this matrix here is really given by V transposed. And this is really a low-rank third-order tensor, right? That's this thing here. And, of course, if you do this, you kind of can reduce the severity of the entire memory footprint a little bit. But it's still bad enough, because if we have, let's say, 1 billion dimensions, and that's a small computational advertising model, typical dimensionalities might be 100 billion. And you might have 100 billion observations. So that's kind of where you need to aim for. But basically, this is a memory hog. So the obvious question is, can we actually reduce this? Mind you, if Steffen Rendle had actually called his model not factorization machines, but deep recommender networks, he would have gotten probably 1 or 2 orders of magnitude more citations, because that's really what it is. It's basically embedding of sparse data in some lower dimensional space, and then a nonlinearity after that. Okay. That said, it actually covers a lot of cases that people have done individually before. So recommender systems, of course, feature-based models, time-dependent models, and yeah, computational advertising. You can all view them as special cases. Now, what happens is really, remember we have this problem that we have our embedding matrix, and this embedding matrix can be huge. So even in the case where we have 1 million here, so that's small, and we have 1,000 here, then, well, this is going to be still, you know, a billion variables. And if I need to store that in memory, I'm talking about 4 to 8 gigabytes of memory. So this is bad. So one thing that you can do is you can basically use prefetching to deal with that issue that you might not have enough memory. So you basically, you spread things out over multiple machines. You then go and have each individual machine request, and since we have a power law, it means that most keys are most of the time not needed on any specific machine. So again, the data actually works in our favor if we just use it correctly. Because the things that we need all the time, we will probably already have, and the infrequent things I just pull in on demand. So that's what happens here. And so then I prefetch the corresponding parameters, perform the updates, and then push the updates back. Right? There are lots of other tricks in there, how you can deal with regularization and mini batches and so on. I'm not going to go into this because it's really just about the data. So just bit of background about how you would actually go and exchange things on a parameter server. Well, it pretty much works just like your network, except that now the switches are replaced with computers. So when you design a network nowadays, you basically have a rack, you have a top of the rack switch, and that then connects with a number of different switches on the top in order to get good cross-sectional bandwidth. We do the same thing in terms of parameter storage. So each of those machines here basically has a shard of the model. And then the workers just request parts of this model from different machines. And there's a lot of nice math on how you can lay it out automatically. And pretty much everybody has converged to that by now. Okay. Now back to the model itself. Now, if I were naive, I would basically take this entire embedding matrix here, right? And I would go and store this. And this would cause a lot of memory requirements and a lot of, well, also network traffic for anything here in the tail. But if you think about it, these are features that occur maybe 4 or 5 times. So if I want to go and use 100-dimensional embedding for something that occurs 4 or 5 times, it doesn't make any sense. So I can immediately apply a safe screening rule in L1 penalty and argue that, well, these things have no chance of even existing. And I don't have to do it binary of either having all the representation or nothing. I can basically gradually increase the dimensionality. Okay. And then you put it all together, and it actually works quite nicely, and basically L1 shrinkage, frequency regularization, and other things gives you essentially the same performance as if I hadn't shrunk it. Unfortunately, it didn't work any better, but at least it worked as well. And that's actually a lot of dollars extra here. Okay. And then, yes, it also parallelizes nicely, it works fast, and it does all the things that you'd want. Right. So to get to the last slide just in time, well, basically, sparse power law data is really, really useful. Use it in your statistical modeling because it'll work to your advantage. Use it in your systems design because, again, it'll work to your advantage. So real data is actually a lot nicer than what you usually think, and you should take advantage of it. And if you want to work on that kind of problems, talk to me either today or one of the other days that I'm around. I guess, as you all know, I've just moved to Amazon, as in starting on the 1st of July, so I'm hiring. Okay, that's the